Okay. Now we can start with the class. Basically, we are discussing functions given by power series. Like we are doing the complex integration. So the context is this. We are doing complex integration.
Is there writing anywhere?
Can you see it? Not visible.
No, sir,
Board.
I can see only the discrete one.
Oh, no, board I have shared. Check it.
I can only see the discrete one.
Okay, wait. I think you have to check the zoom because the board is shared. It is also visible in the live stream. Like there is a two types. Or let me share it.
Change or something.
Let me reshare. I am once again sharing the board.
Yeah, so again I can see only the discrete.
White screen.
Discrete, the solution of the discrete one.
Okay. Okay, this like I am writing complex.
Okay.
You can't see this complex. Complex integration.
Change anything.
Yeah, please try like give it a try. Otherwise, I will look in. In the
Oh, so you're on the
whiteboard.
second page. Okay.
Okay, okay. It was the first page.
There are page.
Got it. Now you can see this, na complex integration.
Yes, yes.
Okay. Yeah, because I have made a new page for this. So this is the complex integration which we have to discuss. And in this also specifically we are focusing now on this, that is functions given by power series. Functions given by power series. That is the main agenda for this particular lecture. Now here we have Taylor series and Lorentz series. All that we discuss. So as the name suggests, complex integration means definitely till now we have studied real numbers. Like whatever calculus we studied, we studied that calculus for real numbers. But complex numbers do exist. We do make use of it in engineering. It has no like very wide applications. It has, and since we are making use of complex numbers, that complex numbers may change, and there is a need to do analysis like the calculus of complex numbers. That is what is complex analysis that subject is about. And here we are focusing on complex integration. So for that, first we are building some basics. So any like we know that any mathematical function we can convert it into a series. Any mathematical function, we can convert it into a series. And that we have already studied for functions of one variable, functions of two variable, like single variable calculus, multivariate calculus. We know all that, like Taylor's formula, Maclaurin formula. Similarly, if I have a complex function, I can expand that complex function. I can convert that complex function into a series. And that is what we are learning. Like if we are given a complex number, how to convert it into a series. So now we are focusing on Taylor series. Taylor's. Okay. So now let us look at one question. Expand f of x is equal to or f of z, we can say, because it's a complex number. The z is the complex number, like z belongs to complex set. So f of z is equal to 1 upon z plus 1 का whole square. And we have to make use of Taylor series for this expansion. We have to expand this complex function using the Taylor series. Using the Taylor series, we have to expand this function. And we have to expand about, because whenever we apply the Taylor formula, it is always good to specify the point about which we want to expand it. About z is equal to minus. Now let us solve this. So in order to solve this question, the first thing is that, okay, whatever the points are given, according to that, we can assume that z plus I is equal to omega, because z is equal to minus I. So z plus I am treating it to be omega. Then z will become omega minus.
Yes.
This is the first step. Now what I can do, whatever function I have given, I can just replace this z with omega minus I. So whatever f of z I have, I can write it 1 upon, like this is the function I have. I can write it 1 upon omega minus I plus 1
Plus one.
whole square. Okay. Now this now what we can do, this 1 minus I can write it like this. 1 minus I plus 1. I just reshuffled it. Isn't it?
Yes.
Now 1 minus I can take outside. Or I can say that I can multiply and divide by 1 minus I, the denominator. So 1 minus I, if I multiply and divide, I will get 1 plus omega upon 1 minus whole square. And this will be square. Because here a whole square is there now. So if I am taking 1 minus I outside, I will be taking 1 minus I ka whole square outside. Or I am multiplying and dividing by 1 minus I ka whole square. anything you can interpret, but we will get this, and this is understandable. We can understand this. This is clear. Now I can write it like this. This will be equal to 1 upon 1 minus I square. And this, if I take it to the numerator, it will become 1 plus omega upon 1 minus I to the power of minus 2. Isn't it?
Yes, sir.
And we know how to expand this. It will be 1 minus 2 omega upon 1 minus I. Then plus, alternating plus and minus. 3 omega upon 1 minus I ka whole square.
So 2 omega is coming.
This is the formula, no? Like we are expanding this. 1 plus, it is minus 2. So it will be an infinite series. Minus 4 omega upon 1 minus I cube. And so on. Why it is an infinite series? Because it is in the denominator, minus 2. And in the denominator, if the denominator keeps on increasing, the something like that is happening. Like we have already seen this. If you remember, we have seen this formula. Once again, I will tell you. Like you have to remember. What I am trying to say is that 1 like a plus b to the power of minus 2. The formula is a minus 2 times b plus 3 times b square minus 4 times b cube plus 5 times b to the power of 4 and so on.
Sir, there is no 1, 2, 3. It's only cube, square, and 4.
No, 1, 2, 3 is there. No? It is written. It's there. You check, it's there. Okay. You cross check it. It's there. Then we can simplify it. Okay, here though we have 1 minus I ka whole square. So it is a minus b ka whole square. This. So here though we can apply that formula. A square plus b square minus 2ab. It will become 1 upon a square plus b square minus 2. And this will become 1 minus. Now instead of omega, I can write z plus I. So 2 upon 1 minus I. Instead of omega, I can write z plus 3 upon 1 minus I ka whole square. Once again z plus whole square. Minus 4 upon 1 minus I cube. Z plus I cube. And so now you can see here I square is minus 1. We know that I square is minus 1. So plus 1 minus 1 will cancel and it will become minus 1 by 2y. Minus of 1 upon 2. And we can simplify it further if I multiply and divide by I. then in the denominator I will get I square, and I square is minus 1. So it will become plus 1 by 2 I, or it will become I by 2. So directly I can write it I by 2 because I know the simple that I can write it I by 2 with this. Okay. So this is what. So this is the required expansion. So whatever function we have, 1 upon z plus 1 square, we can expand it like this. Now we will do the same question using the Taylor's formula. Now we will do the same problem using the Taylor's formula. So first let us write the Taylor's formula. Solving the above problem using Taylor's formula. Or Taylor's theorem. Okay. So Taylor's theorem we know. So Taylor's theorem is something like this. And it is for complex numbers. For complex functions, the Taylor's formula is something like this. F of z is equal to f of a plus summation of n is equal to 1 to infinity. F of n times we are differentiating the function at point A upon n factorial. Then multiplied by z minus a to the power of n. Yes, that's right. So this is the Taylor's theorem. Now we will apply this same theorem for the function 1 upon z plus 1 to the power me. The function is 1 upon z plus 1 square. We'll apply that. So now the question which is given to us in that f of z is equals to 1 upon z plus 1 square. This is given to us. And we have to expand this function. Now we can find f of z. So it will be minus 2 upon z plus 1 whole cube. Because if we take it to the numerator, it is z plus 1 to the power of minus 2. So x to the power of minus n, the differentiation of it will be minus n x to the power of minus n minus. We applied the same formula to get the f dash z. Similarly, we can get the f double dash z. it will be minus 6 upon z plus 1 to the power of 4. Okay, it will become plus 6 here. Because minus 3 is there, na? Plus 6 it will be. So plus 6 upon z plus 1 to the power of 4. Okay. And so using this and using the formula, now we can like substitute it. Now in the question, it is given that we have to expand this series about the point, and that point is z is equal to minus. And here in the Taylor's theorem, this A is the point. So I can say that, so A is equal to minus. So f of z will become f of A, that is f of minus plus summation of n is equal to 1 to infinity f of n minus I upon n factorial. Z minus of minus I plus I to the power of n. Now see, function I know, so f of minus 1 will be, f of minus I will be 1 upon minus I plus 1 whole square plus f dash f of minus I upon 1 factorial into z plus I to the power of 1. Then we have plus f double derivative minus I upon 2 factorial z plus I to the power of 2 and so on. Okay. Taylor's formula we have applied and we got this. Now we can do proper substitutions to get some answer. Now we have already seen that 1 upon 1 minus I ka whole square. It is 1 upon 1 plus I square minus 2I. It will become, see, I square is minus 1, so plus 1 minus 1 will become 0. It will be minus 1 by 2I. I can multiply and divide by I. I square will once again become minus 1. So it will become I by 2. Like minus minus, it will become plus. So we will get I by 2. So this term we saw just now, it is I by 2. This is I by 2. Now f dash minus I. So f dash z is minus 2 upon z plus 1 q. So I can write minus 2 upon minus I plus 1 q. 1 factorial is 1 only, and I can multiply it with z plus. Similarly, f double dash is minus I. So it will become 6 upon, instead of z, I have to write minus I plus 1 to the power of 4 into 1 by 2 factorial is 1 by 2 into z plus I square and so on. Okay.
Yes, sir.
I by 2 minus 2. I can write 1 minus I whole cube. So it will become 1 minus I into 1 minus I square. I can write like this. And in the numerator I have z plus I. Then I will get plus 2 ones are 2 3 3 z plus I square upon I minus 1 square I minus 1 square. Because power 4 is there, so I can write I minus 1 square I minus 1 square plus dot dot. This I can separate. Now what we will get is I by 2. We have already seen that 1 upon I minus 1 square was I by 2. So I can write minus I by 2 into 2 upon 1 minus I into z plus plus here also I have 1 minus I square and 2 times I have. So I can write I by 2 2 times. I by 2 into I by 2 into 3 z plus I square plus dot dot. Okay. Now I can simplify it a bit. Now what I can do I by 2 I can see it is present in all the terms, like one first term, second term, third term. I by 2 I can take common. I by 2 I can take common. 1 minus 2 2 will cancel. Z plus I upon
But 2 to where cancel?
this C.
No, it will be 2. 2 will be there.
2 is there na, in
We are
numerator.
taking I by 2 common, no? Yeah, this 2 will be there in the series.
Sorry, sorry. You are absolutely right. You are right. Yeah, we are taking I by 2 common, so this 2 will be. That's that is very nice. Perfect. And here one I by 2 we will take outside. So we will have I by 2, or I can say 3 I by 2. So this 3 or 3 by 2 I. Z plus I square. So this is
So
what we will
3 1 minus I. 3 upon 1 minus I.
okay. No, so see here, uh, when we are doing the double differentiation, we are getting to the power of 4. So we are breaking it as 1 minus I square, 1 minus I square, like 1 minus I whole square, 1 minus, and 1 minus, like 1 upon 1 minus whole square is I by 2. So that's why I am writing I by 2 two times. Okay, I can do like this. I can once again write this I by 2 as denominator. Like I will only take one
1
one
I
upon,
by
yeah,
2.
I by 2, and this I can keep it as it is. And if I do so, then whatever you are telling, that I can, then I can write, isn't it? And this I will.
Yes.
Now let us compare it with what we got earlier. Just a minute. Yeah. So see, I will highlight it. So this is what we got earlier using the other method, and this is what we got using the Taylor's method. And I think it is exactly same. I by 2, 1 minus 2, z plus I upon 1 minus I plus 3, z plus I square upon 1 minus I square plus, and so on. And it will go so on. It means that, okay, whatever we did, that is right. I hope it is clear. So now we will discuss. So this was Taylor series. Now we will discuss a new series, that is the Laurent. Laurent series. So let us look at it. What it says. So let us suppose we have fz, which is an analytic function. Okay. In a ring Or
I think Lawrence series is easier than Taylor series.
sorry.
Lawrence series is easier than Taylor series.
Yeah. So we have an fz, which is an analytic function in a ring shaped region R. So we have a ring shaped region. In the ring shaped region means two circles will be. So two concentric circles will be there with radius R1 and R2. So we will be having a circle C1. C2 is the another circle. I can say the circle with radius R1. R1. Small, I can small R1. C2 is the circle. With radius R2. Let us do something like this. We can draw it, understand it. Make it a good side. So we have two concentric circles. This is, let us suppose, the center. Let us suppose this is R1. This is R2. Center, let us suppose it is A. And here definitely R1 is greater than R. And we have the R, like the analytic function is defined in this region. So we will say that the main property mathematically for all Z in R, like for all the complex number in this region defined by these two concentric circles, the ring shaped region which we are talking about, all the complex numbers lying in this region will satisfy this formula which I am writing. That is the Lorentz formula. F of Z is equal to A naught plus A1 Z minus A plus A2 Z minus A square plus dot plus B1 upon Z minus A plus B2 upon Z minus A square and so on. So this is the expansion, because Lorentz series is also used for expanding the function. So any complex function, we can expand it using this formula. And the nth term of this series that is the an. Because in any infinite series or in any series, another term plays a very important role. Another term is 1 upon 2 pi I. Integration f omega upon omega minus a to the power of n plus du. And here bn is equals to 1 upon, because see this in the Lorentz formula, this series it is exhibiting two patterns. One is this pattern, it will go, and one is this pattern. So both are different. So an is the nth term for the first pattern, and bn is the nth term for the second pattern. Okay. So let me write bn properly. So bn will be 1 upon 2 pi I integration C2 f omega upon omega minus a to the power of n minus n plus du. Okay. And here this C1 is the circle one. I will mention it. The bigger circle that I am calling as circle one. The smaller circle I am calling as circle two. And we sweep this area in the anti-clockwise direction. Because see, what is integration? Integration is the summation of points. So here in the circle, whatever points is lying, we will sum it. And we will be doing that in the anti-clockwise direction. So when we are integrating all the points in the circle C1, we will be integrating in the anti-clockwise direction. And this is the Lorentz expansion of function, complex function at z is equal to a. Okay. Because here this a0, a1, this is different. And this is the a we are interested in. This is the point about which we are expanding this function. Isn't it?
Yes, sir.
So the idea is very simple. Like let us suppose I have a complex plane. Any particular point, I have a complex function at any particular point, I want to expand it. So I will draw two concentric circles around that point. And all the points lying in this region, I will be using it with this formula or this analysis to expand the function. That is what we are doing. Now let us look at its applications, like how to solve problems. That is what we are interested in. Some questions. The first question. F of z is equal to 1 upon z minus 2, like 1 minus z and z minus 2. This is the function. This is the complex function given to us. Region is given. The region is this. Let me write it. And we have to find the Lorentz series for this function. Okay. So let us give it a try. Like how to do such questions, let us see. In this question, the function is given to us. And see, the interesting thing is the region. And here we can see that we can get an idea about the range. We can call it like the two concentric circle we have. So this might be the radius of the C1, and this is the radius of the C2 circle. And all the points in this interval, for all the points in this interval, we have to expand this function. So here I can draw two circles. A small circle and a big circle. This is one. This is two, the radius. And definitely in this region, the function is defined and function is analytic also. Like how to check for analytic, that we have already covered. I will share it with you. In one of the videos, you will get it. I will share that with you. There is a way to test whether the complex function is analytic or not. It has to follow some properties.
Yes.
And yeah, and very important, whenever we are applying Taylor's series or Lorentz series, the complex function has to be analytic. It's mandatory. So here we can say that f of z, the given function, it is analytic in the range. f of z.
तो इसमें तो हमें तो कुछ करना ही नहीं है ना, इसमें तो हमें डायरेक्ट सॉल्व करके सीरीज निकाल देनी है।
हाँ नहीं, बट ये आपको दिखाना है क्योंकि ये कंडीशन है ना। जब हम when we were proving this or we were looking at this formula, here it is an assumption which we are taking that the f of z which we are trying to expand, it is analytic. It has to be analytic. It's an assumption. So the good practice is that whatever function we have, it is very good to show first that okay, it's analytic. Then let us try to expand it. Let me write it properly. Just a minute. So here f of z is analytic. In the region, in the given region, or in the region one z 2. Now let us apply the Lorentz formula. So before that, we can simplify this function a bit. Let us do that. F of z is 1 upon 1 minus z, z minus 2. Now I can write it minus 1 upon z minus 1, z minus 2. Like this. 1 minus z, I made it z minus 1. So hence I got 1 minus extra. Now I can apply the partial fraction. I can break it into partial fraction. So it will be 1 upon z minus 1 plus or minus 1 upon z. Then we will get the same. Now what I can do, I can take z outside, 1 minus 1 by 0. And here also, I can take z outside. Or here I can take 2 outside. It will become z by 2 or to be more precise, what we can do, I can take 2 outside. I can write 1 minus z by 2 with a plus sign over. How I am able to do that? This z minus 2, I am taking 2 minus z. So 1 minus I will get, it will make it plus. Now what I can do is, I can write like this, 1 by z. Let me write color, so that it becomes more readable. So it will become 1 by z, 1 minus 1 by plus 1 by 2, it will power minus 1 minus z by 2 to the power of minus. And for this, we have a formula. Let us try the expansion of this. That will be 1 plus 1 by z plus 1 by z square plus dot dot plus 1 by 2 1 plus z by 2 plus z by 2 whole square plus dot dot. This is the Lorentz series.
Yes, sir.
So I can underline it. But this is the answer. Okay. So this
Yes,
is
sir.
clear. Yeah. Now let us look at some more questions. And this is relatively easy, as you mentioned it. Let us look at. So we have the function f of z is equal to 7z minus 2 upon z plus 1 z.
सर एक और क्वेश्चन होगा इससे पहले.
Yeah. So that you try it, and I will help you if you find any difficulty. Same way, you give it a try to that. Let us discuss this. So function is given to us and we have to expand it. And this function is defined in the region. Okay. Or not defined, but like this function is given, we have to find the Lorentz series. In region one mod of z plus 1 less than. This is what we have. Okay. Now, whenever z plus 1 is given, like here, first we have to simplify this a bit. So let us do that. Let z plus 1 is equal to w. Then z will be w omega, we call it omega. Now it is given that it is given that isn't it? It's given. Now what I can say is that I can break it into two entities. I can say that mod of z plus 1 is greater than 1, and I can also say that mod of z plus 1 is less than 3. Now what I will do, I will bring this z plus 1 down. Like I can say that 1 upon mod of z plus 1 is less than,
Yes.
and I can say like this, mod of z plus 1 by 3 is less than 3. Now instead of z plus 1, I can write like omega. It will become 1 upon omega mod is less than 1, and omega by 3 mod is less than. So this interval we get. So now we can convert this into the form of omega, where the interval also be one. And before that, we can do one more thing. We can break this function into partial fraction. Then we are good to go.
Yes, sir.
Then we are good to go. F of z is equal to seven z minus 2 upon z plus 1 z z1. When I break it into partial fraction, 1, so I will get like z. Another is like z plus 1. And one more is z plus 2. Z minus. So you give it a try, partial fraction, and let me know if you face any
सर
difficulty.
निकाल लेते हैं, वैल्यूज आ रही थी.
Okay, nice. So you were getting the same value. That's nice. So now this is the f of z which we have to use. Now this is the f of z which we have to use. So now the function we got, and one more thing we can do. All the z we can
Just write
replace
the
it.
z in the omega form.
Omega. Let us do that. So f of z will be, okay, z is omega minus 1 upon omega minus 1 minus
3
3
by
upon
omega only.
omega only, because minus 1 plus 1 cancel, plus 2 upon
Omega
omega
minus 3.
minus 1 minus 2 will be, that is. Now we can simplify it with a traditional way, like here we can take omega outside the denominator. 1 upon omega we can take outside. 1 minus 1 by omega minus
So
3 by
here
omega.
the omega 1 minus 1 by omega, the minus sign will be there.
Yeah. Because we are just taking omega outside.
Yeah.
Or you can consider as multiply and divide by omega.
Okay,
So-
then
so-
no negative sign will be outside.
No, no negative sign. So we are just multiplying and dividing by omega. That's it. So omega by omega will be 1 minus 1 by omega. Isn't it?
Yes, sir.
And here 3 we are taking outside.
Here the minus sign will be there.
Omega by 3 minus. Or what we can do? Yeah, let us do like this. Let us add one more step. It's fine. So first I will take 3 outside. It will become omega by 3 minus. Okay. Now what I will do? I want to make it in the form of 1 minus omega by 3. So minus I will take outside. Then it will become 1 minus omega by 3. Let me do that. It is 1 by omega, 1 minus 1 by minus 3 by omega, minus 2 by 3, 1 minus omega by 3. Now what I will do, just after this, one by omega, 1 minus 1 by omega to the power of minus 3 by omega, minus 2 by 3, 1 minus omega by 3 to the power of, isn't it?
Yes.
Now we can like expand it. Now we can expand it. 1 by omega. Here all the terms will be positive. In the series, it will become 1 plus 1 by omega plus 1 by omega square and so on. Minus 3 by omega minus 2 by 3. And here also all the terms will be positive. 1 plus omega by 3 plus omega square by 9 and so on. Now what I will do, I will multiply this 1 by omega inside this. It will become 1 by omega plus 1 by omega square plus 1 by omega cube plus dot up to infinity. And this minus 3 by 2 also I will include here, minus 3 by omega. Minus 2 by 3. And this will be as it is.
So we'll include in this only.
Yeah, because now we can simplify this now. 1 by omega minus 3 by omega we can do. That we will do. Because
Yes,
this
sir.
term and this term we can work up.
Minus 2 probably.
Yeah, so it will become minus 2 by omega. That's right. That is right. Minus 2 by omega. Minus 2 by omega less 1 by omega square plus 1 by omega 2 plus dot dot. Isn't it? Minus 2 pi. 1 plus omega by 2 plus omega square by 2 plus dot. Now, this is not the final answer, very important. We have to do because omega,
To replace z plus 1 in the
yeah,
series.
yeah, we have to get rid of the omega in the final answer. So we can get rid with this. So what was omega?
Z plus 1.
Okay. Instead of omega, we can write z plus. That's because we saw that z is equal to omega minus 1, so omega is. That is right. This is one series we will get and one more series. Z plus 1 by 3 plus z plus 1 square by 9 plus dot dot. This is the final answer. Okay. So we completed this. Today, we looked into one question of Taylor series, like functions given by power series, and we looked into Taylor series and what is this Lorentz series about, the concept and some questions we do to get an idea how to solve problems. Okay.
Yes, yes.
So now we are concluding this session, the live stream.
So,
Yeah, 1 minute.
hello.
Yeah. So I ended the live stream.
Hello.
No. Hello, am I audible?